Physical science time, let's talk about waves. We're going to talk about waves in general. You've heard of, there are some examples of waves that you've had in your daily life. What's one way that, just as a word, Roman, be quiet please. What's one way, just as a word, that we use the word wave? Yes, wave.
Sound waves.
Sound waves. You've heard of sound waves. What are some other ways?
Microwave.
Microwave.
Radio waves.
Radio waves.
Nuclear waves.
Seismic waves. But you can also think of the waves in the ocean. For instance, Tammy, please, it's time to pay attention. You can also think of the waves in the ocean, or like if someone waves at you, that's a wave. And in all of those cases, it's more apparent in the ocean waves, or when you're waving your hand. But what is a way that we could define wave that encompasses all of those things? So in general, we're going to make a basic definition together of a wave. Okay, so let's phrase it. You're not wrong, Kylie. But let's phrase it a little bit more scientifically. She says moving back and forth. How could we phrase that? What is the verb that's doing?
Moving to
Pushing. Vibrating.
Kind of. Let's use I'm going to use the word oscillate and oscillation and let's use an adjective too. A repeating oscillation. A repeating oscillation. So all of those things have, and the thing that always have in common is a repetition. There's a repetition there. I'm doing it more than once. If I just go, you might call colloquially if I do this, or if I'm driving my car and I go, that counts as a wave, as a gesture, but it's not waving. In the same way, if throughout all of history in the ocean only one wave had ever happened, that wouldn't really be repeating, and we wouldn't really call it. I mean, probably wouldn't have a name for it because it only would have happened once. Anyway, so waves are repetition. That's like the core of a wave, is that it repeats. It has to be a repeating pattern. Waves always transfer, fill in the blank. What do waves always transfer? Energy. Waves always transfer energy. And sometimes matter can move along in a wave. I didn't phrase that great. I can't think of a better way to do it though. But sometimes the wave is traveling through matter, basically. That's not always the case. Not every kind of wave travels through matter, but sometimes this does happen. Waves always transfer energy, but sometimes that energy is transferred through matter.
So,
Yes.
like, you putting up a statement by the pool, and we can hear it in the pool.
Yeah. In that case, that specific kind of wave is being transferred through matter, and that specific kind of wave, a sound wave, does have to travel through matter. Not all waves have to travel through matter, but depending on the type of wave, it either does or does not need what we call, what's the word we call for what a wave travels through? Say it again. Medium. Let's define that. A medium is the, let's just do it like Kyler. The stuff
Why did you have to target me in that?
through which, because earlier you had said a definition of wave, which was right, but we needed to make it sound like a scientist wrote it. But no, this is fine. The stuff through which a wave, you did a good job, Kyler. I'm proud of you. The stuff through which a wave, fill in the blank again. Yeah, I was going to say that, but I kind of like that better, but it is your birthday.
No, we can use transfers because
Oh,
it's
great.
a little more scientific.
Let's find a better word for stuff, too.
Oh, matter.
Hey, as a side note, as a commercial break, I
So
hate
that
myself.
much.
As a commercial break, as a side note, why did I phrase through this? You wouldn't say this sentence this way because you live in Crawdad. The stuff through which a wave transfers. You never say anything like that.
Yeah.
You say what the wave travels through. That's what you would say. Why did I phrase it like this?
Because it sounds like
Because we don't, most people don't.
No,
really
there's kind of a semi-archaic rule in English that we don't ever end a sentence with a preposition. So through is a preposition because it connects two ideas. We don't ever do that. We're not supposed to in English, so I'm very careful not to. Like my board over there, the things that says things of which Mr. Kime is proud. I didn't write things Mr. Kime is proud of because of is a preposition. So there you go. There's your English for the day. Now the commercial break is done. The stuff through which a wave travels. Let's find a better word for stuff though.
I know it's much, but I don't think it's a synonym.
Object is maybe not wrong, but I like that even less than stuff.
things.
Ooh, I hate that one.
Matter. Items. Crap.
We could use matter. Well, but the problem with using matter is that we do consider the vacuum of space to be a medium. The entity. There we go. Entity.
I don't know what that word means.
Entity.
So I'm just gonna leave
Entity
stuff.
means stuff.
I'm just gonna
Entity
stuff.
means a thing that that's the, basically entity is like another word for noun. The stuff through which the wave travels, the entity.
I think I'm good.
Y'all are entities. Can a wave travel through you?
Yeah. So
Um,
wave your arm move?
Here's an example of a wave traveling through a people's. Sometimes I'm gonna draw a little picture here.
Wave.
This was supposed to be my wife.
Oh, that's a baby.
No, that's not a baby. It's a microphone. What kind of drawing is this? She doesn't hold the baby like this.
Wait.
She's like it's a can of mayonnaise. No.
You hold the baby by
Fire
the neck
mayonnaise.
or by the legs.
Okay. It's supposed to be a dadgum microphone.
A parrot?
It's a
I
microphone.
thought you said a carrot. So it's.
She has hair.
I
That's why I
Jenna you
did
drew
that.
her like that.
Okay. Anyway. Okay. So sometimes Mrs. Kime, don't call her by her first name, Tyler. Sometimes she's. Listen to me, please. Sometimes Mrs. Kime is on the stage, and I'm back here running the sound system, and there's a little like receiver.
Since when?
What kind of question is that, Wade? There's a little receiver back here because this microphone is wireless. It's a wireless microphone. So how does it transfer information?
Bluetooth.
Okay, Bluetooth are waves. This one isn't Bluetooth, but this one is a wireless microphone. It's transmitting them at what kind of wave?
Waves. FM. AM.
AM or FM what?
Hey.
Microwaves. Radio.
Radio. It's probably true. It's transmitting them as radio waves. And when there's a bunch of bodies, usually living bodies, between, so far always, as far as I know, when there's a bunch of bodies between that and that, the waves just go right through them. Same thing in this room. In this room, there are microwaves permeating every single space of this room. Not microwave ovens, but the type of electromagnetic waves called microwaves permeate this entire room because cell phone towers use microwaves to transmit signals. That's obviously happening here. Wireless internet is transmitted through microwaves. All kinds of other stuff.
But we still don't have service everywhere.
But the waves that make up that are the medium through which they're traveling is air, obviously, but it's also traveling through your body. It's traveling through this music stand. It's traveling through the radiator. It's traveling through the air conditioner on the ceiling. It travels through matter. Some waves can travel through matter.
So like it's
Not always. Well, not
So
always.
So
And
like
not
when,
all. Go ahead.
when my mom's car is on and it's parked in the driveway and I'm upstairs close to that window, my phone connects to her car.
Yeah, because the waves that allow that connection to occur are traveling through not only the air, but through the wall and the
Yeah.
electrical outlet. And all
So
that.
then why isn't
Listen, Carter has a question. Carter raised his hand when he had a question. Carter, let's hear it.
So how come like some areas have no service? Like, is it
Right, so even as if this is the cell phone tower,
it's sounding
what happens to the waves as they get further from the cell phone tower? Yeah, they get weaker and weaker. It spreads out. It's kind of like when there's a ripple in a pond. The waves are still there, and in fact they're the same. Like if you added up the magnitude of this entire wave that's coming out from the cell phone tower, it'd be the same as this one nearby. It's just spread out more. And so the further from a cell phone tower the microwaves get,
Hey, is
the
that how
less
Life 360
the less
works?
information they're able to carry. And since they're digital waves, it's either yes or no. Either they do carry information or they don't. Either you do have service or you don't. Yes.
So say like you're at Box Butte and you're down by the water, you have no service, but once you walk up the hill, you do.
Right, probably because that's
that's
somehow closer to, or there is less blockage between you and the cell phone tower. I would say.
so
That's why people raise their phone again.
Yeah, that's not how.
why is there dead zones?
We just talked about it. Okay, let's move on. So a medium is entity through which a wave can travel. And there are different kinds of waves. Let's talk about the different kinds of waves. I'm going to erase this, and while I do, I'm going to start talking about the different kinds of waves. What would be a good heading to put in your little notes?
Kinds of waves.
Kinds of waves, or types of waves,
Types of waves.
or categories of waves. This is the things that we have already. Please, I don't know why you think you need to keep talking. Stop talking. The things we had already written about waves in general are true for both of these kinds of waves. The two major kinds of waves, the two categories of waves that we talk about, categories of waves. So there are, I'm going to say categories for sure for this because there are different types of waves. I would call a type of wave like, for instance, a sound wave is a type of wave. A microwave is a type of wave. Visible light is a type of wave. But there are different categories of waves into which many of those types of waves fall. And the two categories that we're going to talk about are transverse waves and longitudinal waves. Leave a lot of room because we're going to draw a little diagram for each. So I'm going to write a little description, give a couple of examples, and then draw a diagram for each. You probably already recorded this in your notes, right? You know what these things are, is that correct?
Yes.
The main difference between these two things, the main difference between a transverse and a longitudinal wave is how the medium moves as distinct from how the energy is moving. So in a transverse wave, the wave motion is perpendicular to energy flow. So if the energy is flowing from left to right up here, there are two ways that this wave motion can be perpendicular. How can I draw this wave? There are two ways in three-dimensional space that something can be perpendicular to the line from this to this. What's one way that could be perpendicular?
They're going in the same direction.
No, it can't be going the same direction because that's not perpendicular.
Oh, it's parallel.
Up and down. That's how we probably will draw. That'll be the easiest way to draw it. So you see the wave motion is up and down. What's the other way I could have drawn it to be perpendicular?
That's what I meant to have them going.
Upright. Can you do that?
Say it, Lily. No. On this, so left-right is one axis. I have my energy flowing from left to right. Up-down is another axis. What's the third axis in three-dimensional space?
South, and then
Diagonal.
We might draw it diagonally.
You're distant from back.
There you go. Yeah, forward and back. So if I can't because it's a marker, but I can't I would draw it in and out of the whiteboard. Anyway, wave motion is perpendicular to energy flow. So the wave motion in this case is up and down. The energy flow is left to right. What's an example of a transverse wave? You might remember from your book. Example? All what? All kinds of.
Energy, matter, waves.
Okay, no. So you stop. All kinds of what waves are transverse waves? There are more than just these.
Radio.
Yeah, that's true. But sometimes, be more or less specific. That's not a real thing.
Electromagnetic wave.
All the electromagnetic waves. Remember, electromagnetism was one of the four fundamental forces of the universe, and electromagnetic waves incorporate what kinds of light? All the kinds of light, but what are the kinds of light?
white light, black light.
Let's name them.
red light.
No, just be quiet. Let's name them in order from the lowest frequency waves to the highest frequency waves.
Black light.
What's the lowest frequency electromagnetic wave? You have a chart of this. You took notes yesterday. I know you did. So someone should know this. What's the lowest frequency electromagnetic wave?
White light.
Radio.
What?
Radio.
Radio wave. Then?
Micro.
Yes. Then?
Water.
Yeah, you got it, Roman. I don't know where you're getting this information from. Infrared is next.
Ultraviolet.
No, you're missing one. Infrared means below red. Ultraviolet means above purple or above violet. So what's in between those?
Red.
And?
Violet.
And?
Rainbow.
And? Yeah, what do we call the rainbow? All the rainbow colors are
White
Light.
light. Visible light. We sometimes specify visible light because that's the light we can see. Visible light. Then
What's the light we
then
can't
the higher frequency, all the other ones, the higher frequency above visible light would be
Ultraviolet.
ultraviolet. Then?
Gamma rays.
That's not the next one, but yeah, you're right.
X-rays.
X-rays,
X-rays.
and then gamma rays.
Gamma.
Yeah, because camera rays take a lot.
So all the electromagnetic waves are transverse waves. And just as an FYI, if the energy is flowing from left to right, we could say that the electricity, the electro part of the electromagnetic wave, is flowing up and down, and the magnetism flows in and out. They're perpendicular to each other too. Just so you know, because electromagnetism is both electricity and magnetism. Magnetic waves travel also perpendicular to the energy, but it's the other perpendicular. So these things, energy, electricity, and magnetism all travel perpendicular to one another on the three axes of space. Let's label this while we're here. What are the high points of a transverse wave called?
Crest.
The low points?
Drop.
What's this thing in the middle called? The thing that goes along the...
The axis.
Sure, yeah, it's sometimes called the axis. I've heard of it called other things too. Let's think some of them. I forget what your book calls it because of your other things.
Rest position.
Rest position. Put your chair down, Wade.
Equal.
Put your chair down, Wade.
Equilibrium? Is that?
Yep.
That's
Hey,
what Wade
that's
said.
what
No, we can't break it out.
The origin, the baseline. It can be referred to as many different things, and it kind of depends on the kinds of waves. For instance, for ocean waves that are traveling as transverse waves, we might call it rest position, whereas for electromagnetic waves, we usually call it the origin. Anyway, the distance from origin to the height of the highest crest or the depth of the lowest trough is called what?
A pit.
The height of the wave
Crest.
would be called the, no, that's
Oh,
I don't even
frequency. Amplitude. No.
amplitude. The distance from one crest to the next, that's the wavelength. And you should be aware that this is abbreviated with the Greek letter gamma, the Greek lowercase letter gamma.
GI.
You said that in the book.
Yep, that's I'm sorry, not gamma. Lambda. Same as half-life was. I was thinking about gamma from gamma rays earlier. Forgive me. This is the lambda. Lambda. And there's one other property of waves, which is its frequency, which we sometimes, depending on the kind of science we're doing, it's always called frequency, but we sometimes abbreviate it with the Latin letter F, which is just our normal letter F, or we sometimes abbreviate it with the Greek letter nu, which is the kind of like the Greek version of the Latin letter N. If you're going to draw the Greek letter nu, it's kind of like a V with one flat side and one curved side. It's almost just like a letter V. But this is the Greek letter nu. For any wave, we're going to come back to this, but for any wave, velocity equals the wavelength times the frequency. And specifically for electromagnetic waves, they are always traveling at c, which is, you remember, what's c stand for? You say it.
Speed.
Speed of light. So this is specific for electromagnetic waves. This is true of all waves. Wave speed, v, or wave velocity, v, equal as wavelength times its frequency.
I keep on thinking you say wavelength.
I drew the frequency over here because, well, how do we define frequency? Yeah. The number of oscillations per unit of time. And we measure that in hertz,
So like the
which is
higher
equal to 1 over second.
the higher the sound is, like the closer the frequencies are.
Yep, listen, Allie's right, of sound waves, the higher the frequency, the higher the pitch. We use kind of different vocab for sound waves.
Okay,
For
so
light
that's why,
waves,
like-
for light waves, the higher the frequency, for one thing, it goes this way on the electromagnetic spectrum. But for our visible light, red has a lower frequency than purple. And so when you see something that's blue, that has a higher frequency than something that's red.
What about black?
So frequency, a variation in frequency for visible light results in changes in color. A variation in frequency for sound changes pitch. What do you think the amplitude of this wave might be for visible light, if you had to guess?
1.
So if the frequency...
0.
No, it's not a number. If the frequency represents color, and if we change the frequency, it changes the color of the light, what would the amplitude change of the light?
Like shade.
Yeah.
Yeah, kind of. It's the amount of light. If it has no amplitude, there's no light. And if it's really high amplitude, that's really, really bright.
So neon.
Okay, I have a question.
And then in sound, one thing before you do that. In sound, what would an increase in amplitude be, and that's why it's called that?
The louder it is.
Yeah, the loudness is the same. Is the higher the amplitude, the higher the loudness. That's why the amplifier is amplifying the sound, making the sound volume more. Yes.
Okay, so you just said like the higher the
Amplitude.
louder, you know. But like bass in music, it's so low, so I'm assuming that
That's like 20
but it's so
hertz.
loud, you know.
Yeah, it depends. They can have the same sound volume or the same amount of sound as a high-pitched sound. It just sounds different to us.
Oh, okay.
Anyway, let's move on to the longitudinal waves now. You are responsible for knowing, I call this the anatomy of a wave. You also need to know that for the longitudinal wave. So, if in a transverse wave, the wave motion is perpendicular to energy flow, what do you reckon will probably be true for a longitudinal wave?
Hold on.
Straight.
Opposite.
Perpendicular, vertical,
It was perpendicular for transverse.
horizontal.
Parallel.
Parallel. So in this, the energy flow we could say is still, the energy flow is still, we could say, from left to right, but now, instead of the particles moving, how are they moving in this? Maybe not particles, but the wave was moving how? In this one, in the transverse wave, it was moving how? Up and down.
Up and down.
So
So is
the
it-
energy was traveling from left to right. In this one, the wave itself is traveling up and down, or in and out. But for this one, if it's traveling left to right still,
Oh, it just goes
It's
like
gonna be.
it's going how? How's the wave traveling? Left to
Is it-
right.
it's
Also,
traveling-
it's parallel. It's also traveling left to right. So in this case, the little particles that make up the wave are oscillating in this direction. So we end up with these things called.
Oh, so it looks like a voice recording.
Yeah,
It's like the
heck yeah, it
hospital
does.
type deal. Is that kind of, no, that would be transverse.
Like your heartbeat
Yeah.
sensor.
That's probably a combination of both, and a lot of them are. But yeah, these represent the anatomy of this kind of wave is similar, except instead of having crests and troughs, and we can represent either in either way. But the areas of high activity are called compression. Oops, I'm going to do this in brown also, like I did the transverse wave. Where did brown go? Is this brown? Oh yeah, it is compression.
I heard you.
And then the space in between is called a rarefaction. Oh, your book calls
I
these.
did that wrong.
Your book heads this section compressional waves. That is synonymous with longitudinal waves. In fact, the last sentence of that paragraph even says compressional waves are also called longitudinal waves. You should be aware that these things are also called compressional waves. In the same way, we can still have a wavelength. I really did a bad job of drawing that, but we have a wavelength. We can still have, excuse me, we still have a frequency. We just now have compressions and rarefactions. How would the amplitude be in this, do you reckon?
Very big.
I mean, that's not the kind of question I'm asking.
Measure.
So in this one, the amplitude was how the distance from baseline to the top of the crest. What is it like in this, do you reckon?
Wait till very.
What it is, amplitude in this, amplitude is how different the compressions and rarefactions are. How different they are. So in a high amplitude longitudinal wave, the compressions would have a lot of matter in them, and the rarefactions would have very, very little, almost a vacuum. And in low amplitude, there'd be much less difference between them. That's the difference in sound volume. If I'm whispering to you, if I say,
What?
what that's doing, the sound as it's coming out of my mouth, as the sound is coming out of my mouth, it's my vocal cords are compressing the air just a little tiny bit, and so the compression is pretty is not as compressed as it would be if I say "Hey!"
Oh my gosh.
That makes my vocal cords constrict more, which causes a greater compression and therefore a greater rarefaction. So the bigger the difference. So let's draw another one of these with a bigger difference, or sorry, a less difference. So this would be a somewhat high amplitude sound, but for this one, for a low amplitude sound, we would have them be. It's still the compression is still where they're closer together, but now the rarefaction is they're not that. You see what I mean? So there's less difference between them. That's a low amplitude sound. Does that make sense? Does that make sense?
Yeah.
Real quick, before we finish, we're going to talk about reflection, refraction, diffraction, and interference. So we'll try those things down. Those are all vocab words. Does anyone need this fill up here? You will, just so you know, and we will do a little bit of math together on this, but you are responsible for having this equation, both of these equations. They're the same thing. One's just about the speed of light and one's about any wave. You need to have those equations memorized. And you need to be able to manipulate them. So for instance, while I erase this, I'll tell you. So for instance, you might be given a frequency and a velocity and have to find the wavelength. Or you might be given a wavelength and a frequency and have to find the velocity. You know, like you should be able to substitute and solve those just like we've been doing all year for all our different equations. It's a fairly simple equation to manipulate. It's only 3 variables. Just make sure you follow the steps, right? Write the equation, write the equation, manipulate if you have to, substitute, and then solve. What units should we use? What units did we say that
Hertz.
Yeah, hertz is frequency. And then wavelength is measured in just length units. So something like meters or millimeters or nanometers. And then velocity will be measured in meters per second or centimeters per second. But since hertz are 1/second, multiplying that by a length, meters, gives us meters over second. Reflection, refraction, diffraction, and interference. We have also positive and negative interference. I'm sorry, I phrased those incorrectly. Constructive and destructive interference. Let's start with reflection. You know what this is. This should be pretty easy. And when a wave reflects, what does that mean it's doing?
Oh,
Say it again.
echo.
Echoes and mirrors are both examples of this. But give me, in general, like in a sentence, what happens when a wave reflects?
Oh, that's
Yeah. Bounces
An
back.
echo.
And it follows what's called the law of reflection. If this is the surface, we draw an imaginary perpendicular line called the normal. And whatever the angle of incidence is, if this is angle theta here, then it reflects also at angle theta from the normal.
Theta?
Theta. That's like the standard variable for angles is theta. This would be called the angle of incidence, like it's coming in, and this we call the angle of reflection. So in this case, theta always equals theta prime, which means whatever angle it comes in at relative to the normal, it also goes out at that angle. So like if you're looking in a mirror from over here, it's going to come out over here. We do a fun little lab about this, and we'll do that in all of the video. Law of reflection. What is refraction then? Reflection is when it bounces back. What's refraction, you reckon?
Bending.
Yeah, it's the bending of light.
So it's like,
Oh, sorry, not just light. Bending of a wave due to a change in what? Can you guess?
Direction.
Speed.
Medium. Change in medium. Remember, the medium is what the wave is traveling through. What would the refraction of light look like, and when might it happen?
Oh,
Like in water.
Yeah. When the light goes from traveling through air to traveling through water, it changed medium, and therefore it bends. The light bends. It goes in a different path. So we might see this. Like here's a little cup of water. The light comes in at this angle, and then it goes out at a different angle. There's a difference in angle there. And the difference in these two angles is called the refractive index. There's some trigonometry you can do with that, and we'll do that in physics, but we're not going to do it right now. Refractive index. Diffraction occurs when waves bend around objects. The example your book uses is, there's a really kind of cool picture of some waves, some water waves going past some rocks, and they kind of go around the rocks. So I'm going to do a bad job drawing this, but I'm going to try. So we have some waves here, and then there's maybe a rock there and a rock there, and the wave kind of collides with that rock, and then the rock makes its own little waves coming out also. Same thing down here.
So like with the marbles.
Marbles were more of an example of like the transfer of energy through waves, like we talked about
So
earlier on.
kind of like that. Sort of.
And then lastly, interference is when two waves collide, their properties. I'm just going to put add, because you guys are smart enough, you're progressed enough in your mathematical career that you know if we add a negative number, it's the same as subtract. So the base function is addition. They're always adding, but sometimes it's like adding a negative. We call two waves that have matching crests and troughs, we call these two, yeah, the wave piece.
Equal waves.
No, those two are going to perform, see I wrote these down, constructive and destructive interference. These are in phase. In phase. So the crests match and the troughs match. If they add together, if those waves collide, it's going to equal a wave with higher crests and deeper troughs.
That is why.
That's called constructive interference. That's constructive interference. This thing here is constructive interference.
So
Can you guess then what destructive interference would be?
When they subtract and create.
Yeah, and what might we call
It's
waves
small.
that have that?
Out of phase.
Out of phase. So when waves are out of phase, the crest of one matches the trough of the other, and vice versa. And those would add up to what?
I don't know. Something smaller.
They add up to something smaller. If they're exactly the same frequency except out of phase, then they'll add up to 0, and there'll be no wave at all. They'll cancel out. Mr. Somebody doesn't like when I say cancel out, but you know what I mean when I say it. So out of phase would look like that plus the opposite. I'm just drawing it over the top. Out of phase. And they would add up to nothing. They just add up to a flat line. And then there can be anything in between too. There's not only in phase and out of phase. They can be partially in phase, partially out of phase, and they will add up in a corresponding way. Do you have questions about this? I know we went through it kind of fast, but you also spent yesterday taking notes and watching videos over this. Do you have questions about what we talked about? Let's do the wave. You start, Lily. Let's do the wave. Do the wave.
Throw your arms.
Alexa. Okay, we have to start over. Come on.
Let's
Let's start
going
with
side
We're going to start with
to
Roman and
side.
Carter in the same way.
Guys, are we going side to side or front and back?
3, 2.
Kim, you did it wrong. That was pretty good.
I didn't even want to.
Okay, bye.